días, daros las
Was
gracias
that the
por
video?
estar aquí
Okay.
a prácticamente
Good
casi primera
morning.
hora de la mañana, aunque sean
I
las
would
11,
like
hora
to
local de aquí de España.
thank
Y
to
bueno,
thank you
pues
for
vamos
being
a,
here
vamos a
at
empezar con lo que sería el taller.
the
Para la
very
gente que
first
trae
thing
los
in the
equipos, en los
morning.
laterales hay para poder,
We're going to start with
hay
the workshop
tomas de
for
corriente para que
those
lo
who
podáis seguir.
have a
Bueno,
laptop.
pues un poco sin
You
más,
have a plug
como ya me han
on the
presentado,
sides of
soy
the
Pedro.
auditorium.
Me conocen como
Without
Sauron
further
y bueno,
ado,
pues un poquito pues me
I
gusta
am
la
Pedro.
seguridad.
I am
Llevo
known
unos
as
cuantos años en
Sauron,
ello y me encuentro
and
pues
I like
dedicado pues prácticamente al
cybersecurity.
100%
I've been
en todo
working
esto.
on this field
Pertenezco
for
a,
several
a
years,
CSQ
and
y bueno, pues hacemos como que el que
I'm
dice, pues hacemos
passionate for
prácticamente de
it.
todo, desde formación, auditorías, prácticamente pues
I
tocamos todos los
work
palillos
at
y una vez
CS3
presentado pues
Group,
vamos a
and we
empezar
do
con lo que
almost
sería la parte
everything,
que para la que habéis venido,
security,
con el tema del exploiting.
engineering,
Bueno,
and so on.
vamos a presentar primeramente lo
So
que sería
let's
pues un primer
go
exploit
to
muy
talk
fácil para que
about
entendamos,
exploiting
digamos,
vulnerabilities. But
cómo
first of all,
funcionan los exploits,
we're
¿vale? Para
going
que tengamos
to
esta idea, para
start
que
with a
muchas
very
veces cogemos
easy
código,
exploit
lo
in
bajamos
order
a lo
for
mejor
you
de
to
un
understand
repositorio,
how
nos
exploits
limitamos a
work,
compilar, no
because on
sabemos
many
ni siquiera lo que
occasions
hace.
we take
No es la
some
primera vez
code
que hemos
from a
metido dentro de un
repository
exploit, hemos
and
hecho el
we
exploit
start
y aparte hemos
combining
hecho
it.
alguna
We don't even
otra
know
alguna broma de
how
estas
it
típicas
works.
y como nadie comprueba el código, como nadie sabe lo que hace, pero queremos, simplemente queremos obtener el
Since
resultado,
nobody
como no funciona,
checks
pues nada.
the code
Entonces vamos a empezar con lo que
and we
sería la
just
parte de
simply want to
crítica.
obtain the code,
Después
it
sí que
doesn't
vamos a
work,
pasar a lo que
so what
sería la
do we
parte de
do? Let's
Spectre y
start then
Meltdown.
with the from the
Prácticamente
beginning.
podemos decir que son
We will
iguales.
speak
Spectre, supongo que habréis oído hablar de él.
first about
Ha sido
Vertical
muy
and then
famoso.
about
Además,
Spectre
por ejemplo, todo el
and
tema de
Meltdown, which
aplicación
are
de
very
parches,
similar.
de todas las
Spectre,
cosas que
I'm
nos han
sure you
ralentizado,
have
pues todo lo que
you are
es la
familiar
parte
with it.
de la CPU
It
nos la han
has
ralentizado entera,
been useful.
independiente de todo lo que sería pues
It
su
has
sistema, por ejemplo, del
affected
sistema
the
operativo, que es mucho más,
CPU.
me da
It
igual que
has
sea un
slowed
desarrollo,
it
un Linux,
down,
OS X,
and
que sea
it
un Windows,
has,
cualquier cosa, porque el problema lo
regardless of
tenemos
the
en
operating
el
system
microprocesador,
that we
¿vale?
use,
Soluciones
whether
grandes,
it is
pues que
Linux,
cojas, que tiras tu
Windows, or
ordenador y
any
te
other,
compras uno nuevo
because the
y de nueva
problem
generación.
is in the
Os voy a presentar
microprocessor.
esto, no es lo
So
único, es
people
decir,
in the
pues esto se
end
sigue explotando
end up
actualmente
buying a new
y
laptop.
con nuevas cosas que están saliendo, con
And
lo
I'm
cual pues
going
bueno, muy contentos y que
to
vean
talk
aquí
about it.
pilas, pues para
And I'm
coger y
going to
para,
mention new
digamos de alguna
things
forma,
on the field
poder ofrecernos, a fin de cuentas, ya que
so
compramos el
that
hardware caro,
somehow we
pues a fin
can
de cuentas que sea también seguro. Bueno, sin más, vamos a empezar con lo que es la parte
use the
de Vertical.
hardware
¿A quién
in
le
a
suena?
secure
De los que
way.
estáis aquí, que hay un montón de gente para un taller tan
So without
técnico.
further ado, let's
Las pocas veces que
start
veo
with
tanta gente.
Vertical.
¿A nadie? Levanta
Who
la
are
mano, por
familiar
favor.
with
¿Nadie?
Vertical?
Uno, dos,
It is one
tres,
of the rare
cuatro. Bueno,
occasions when I
pues
see
vamos a ver.
so many people.
Lo que es el
1,
Vertical,
2,
¿vale? Esto simplemente es una
just a few
escalada
of
de
you.
privilegios, es
Okay.
lo que nos gusta. Somos un usuario, un mundo lirondo en un
Dirty
sistema.
Cow
Yo no
is a
tengo permiso
privileged
ninguno, acabo de
escalation.
coger y acabo de
We
entrar
are a
y
user
soy el
in a
becario
system. I do
de
not
la
have
empresa
any
y me quiero
permissions.
convertir en el usuario super
So I am like
administrador,
an
super
intern
poderoso
at a
y tengo que
company,
hacer
but I
pues una
want to
magia, como
become
nosotros decimos,
the
para poder coger y para poder elevar a
administrator
esos
user.
privilegios y convertirnos
So we need
precisamente
to
pues
do
en eso.
some magic in
Esto, por
order
ejemplo,
to
pues es una vulnerabilidad bastante antigua. Si vemos, si hacemos
obtain
referencia a lo
more
que sería el IVE que
privileges.
tiene,
This
vemos
is
que
a
es de
very old
2016 y
vulnerability
afectó, en este caso, pues a todos los kernels
because
de Linux,
it
incluyendo, como
started in
lógico, Android, os
2016 and
sonará.
it
Y de hecho,
affected
pues por
all
ejemplo, con esto,
kernel
aprovechando el
in
duplicado, podemos
Linux-based
rootear perfectamente lo que serían
systems,
nuestro dispositivo,
including Android.
podemos escapar lo que sería la parte de las ambos que tenemos sin mayor problema.
So thanks to
Y
this, we
aunque ese es el
can
objetivo,
root
entonces vamos a ver
our
un poquito todos los
device,
pasos atómicos para
and
poder
even
entender
if that's
realmente
the
cómo y
objective,
por qué
we're going to
funciona.
see all
Bueno,
the
esto,
steps in order to
conforme estáis
understand
viendo ahí,
why and how it
nosotros
works.
el problema que vamos a tener y por lo que se
As you
llamó
see on
el
the
code
screen,
es precisamente del
the
copy on
problem
write. Entonces, con este
ahead
copy
of
on write,
us,
nosotros,
the
como es lógico,
code,
pues viendo y
COW,
entendiendo
is the
lo que sería la
Copyonwrite.
vulnerabilidad, después nos va a dar paso a poder entender mucho mejor lo que son los pasos atómicos, por ejemplo, que
So we
vamos a
need
utilizar
to
tanto en
understand
Spectre
the
como en
vulnerability
Meltdown.
in order to understand the
Pues, consecuencias, como es
steps
lógico,
that we're going to
podríamos
use
modificar,
both
aquí
for
en este caso,
Spectre
cualquier
and
tipo de
for
fichero que estuviese
Meltdown.
protegido, un etc, por ejemplo,
As
password o
consequences, we could
cualquier tipo
modify
de
any
cualquier
kind
tipo de
of
fichero, como si
protected
fuésemos el usuario,
file, such
simplemente
as
el usuario
etc
root, ¿vale?
password,
Tenemos
any
un montón de
kind of
jobs que
file
las
as
tenemos
if we
colgadas
were
en
a
GitHub.
user
Ya os
or
digo,
the
los que
root user. We have several POCs. You can download them from GitHub. Usually people are familiar with this, but they need a workshop in order to understand all these steps. Usually manufacturers launch some patches and this vulnerability disappears. Let's start with a memory mapping of a file. Usually we are going to do it with C language in a very easy way, and we also already have the code written for you not to have a typo error. So let's see how to map a Linux-based system file. In order to map the memory, we're going to use the system called memory map. We can call the system in order to map a device. Let's say a memory device, maybe to write on it, to just read it. It is just opening it, and instead of working directly on the device, I use it in the memory. This is a very simple piece of code with the typical include. And then we go to the standard system code. I guess you are familiar with C language. It is basically like reading up pseudocode. Where in one of the lines you see the numbers on the left. Let's imagine we open a etc host file. We have the possibility to open it in read-only mode or in writing mode. I think I haven't said nothing new so far. We know that when opening a file, there is a subsystem of permissions. If the file only has a read-only mode for the user, for example, the etc password, even if I try to make it, to open it, if I want to open it for writing and read modes, the system is going to tell me that I can't, because the subsystem of permissions is going to prevail. However, I could create in line 2 a memory map of the file. In here, you can notice the modifiers we have. We have the prod read, which are protections in the read-only mode. I have the prod write, which enables me to read and write. And then we have the map shared, which is the shared memory, or a private memory, the map private. So I could read 10 bytes. These are normal operations. You are seeing MEMCP. We have the printf, and if we want, we can clean the code and we can give it back as it was. If we hadn't declared the main, we can take it back to the operating system through void. So we're trying to understand the function mmap.
Memory map que vamos a coger y qué vamos a hacer. El principio lo tenemos claro.
Después, the memory map, what are we going to do? The beginning is easy. Then the kind of protection must match with the permission of the file in the device. if I'm an user and I'm trying to open etc passwd with the read mode, I should use the read protection, because otherwise the operating system would tell me, hey, what are you doing? You're trying to write on this file or override on it. And then I have both memory models, either shared memory or private memory. This kind of memory,
estas transparencias se van a hacer públicas. Después, cuando acabemos el taller, voy a indicar dónde las tenéis para que las podáis.
These slides are going to be published. I will tell you after the workshop where to download this PowerPoint. But how does a mapped memory work, a shared mapped memory? We have several processes. We are using multitask operating systems, and we need to map the memory somehow. But what happens with the physical memory? For each one of the processes, it is thought that the physical memory is theirs. That's why we have the describers and the tables within the operating system, which make the process think to be it is unique and the only one. But what happens in the operating system? Let's imagine you have a first process with a virtual memory. On the right part, we have a second process with a virtual memory. We have a file descriptor, and if we open the same file, both pointers will point to the same place where the file is in the physical memory. Logically, the operating system wouldn't open the unlimited physical memory, and it wouldn't be logical to open two different describers when we're not going to do a lot. We just want to read the data in that file, as is the case of the etc passwd. So what's the difference? I tell the operating system I want to use my private memory. So the file is going to be assigned to private memory just using mat private. The changes are not going to be visible for other processes, but the content of the original memory is going to be copied in the private memory, where I will be able to do whatever I want. So notice how the physical memory works between process 1 and process 2. There's going to be a copy of that memory, so that with my private memory I can work on whatever I want. If I want to modify something, I will be able to do so, but if I'm going to discard, or if I'm going to discard the changes in the file, it should be copied on the original memory, and then permissions are going to tell me you can do whatever you to do in your private memory, but obviously those changes, those modifications in the original file are not going to be copied into the original file, because the operating system is going to prevent it from happening. This is the theoretical part for you to understand the magic we're going to use. Here is where we have all the description, and then let's let's get on working in order to have a practical workshop. So we're going to try to do a small exercise, and first of all we're going to take a code, we're going to try to map a file to do whatever we want. If you have the virtual machine, it has the port 22 open, so that you can use any laptop, because if we had it with VirtualBox, it would have been more complicated to use this console. I'm using DLL in. Here you have all the microcode, and in the first one we find the dirty cow, which, look what we have here. We have the mmap.c. It corresponds to the file that I have mentioned earlier. Super easy. In this case, let's see what we have done. I'm going to open the etc passwd. We are a root user, so we open this file with the read-writing mode. The operating system is going to check it for the root user. Is that correct? But I want to do it as an administrator user. Then I could read those 10 bytes, I could write on the memory, and I could commute modifications. So, oops, I'm sorry. That's quite easy. So root, can you say it properly, or do you need a bigger font? Okay, so root and password.
Aprovecho porque hay otro usuario precisamente que se llama.
There is another user which I am going to use, which is CyberCamp with the same password. CyberCamp password. In order not to open several terminals, I'm going to prepare this user. Or maybe we could open anyone. Let's see. I'm going to open another console. SSH, CyberCamp. The console is ready to work on NAT mode so that you don't have any problem to access it.
172, no se ve muy bien. A ver. Me han dicho que no me diera la vuelta, pero... A ver. Me han dicho que no me diera la vuelta, pero...
I was told not to turn around, but I think I need it.
Tenemos por aquí a 172, 16, 113. Bueno, le vamos a poner... Vale. Paso. Bueno, le vamos a poner... Este usuario... no sé si se ve más o menos por el tipo de letra.
Okay, so I don't know if you can see it, this user, if I write ID, it is an user without any privilege, but if I want to see the content of the file etc passwd, we see everything, but we cannot do anything else. Obviously, I'm not allowed to write. I wish we could do it directly, but it's impossible. Okay, I'm entering here the alias.
Vamos a ponerle pues alias, menos color. Oye, estoy yo bueno. Alias. Oye, estoy yo bueno. Es que no se ve el terminal ahí en el suelo. Vale. Bueno, ahí solamente tengo... Es que no se ve el terminal ahí. Entonces vamos a hacer una cosa y es... lo que sería el código.
So I just have one exploit, and let's do one thing. The code that I have here, the mmap, is going to be copied in home of CyberCamp.
Vamos a cambiarle lo que sería pues el propietario, CyberCamp.
Then this is the owner, CyberCamp, home, CyberCamp, and the file we copied, mmap.
Bueno, aquí, pues, como es lógico, yo tengo CyberCamp, tengo mi mmap y básicamente, pues, a ver,
logically, I have my CyberCamp, my mmap,
voy a intentar abrirlo como lectura y escritura.
And I look at the code again. I am going to try to open it as read and writing mode, and I'm going to try to change it. Let's say gcc -o name mmap, and let's compile the source. Do you think it is going to work? It shouldn't, because if it does work, then it's like winning the lottery. This is a segment breach. It's telling me, hey, you have tried to do something which is not logical according to your permissions, so I'm not allowed to do so. This is the normal behavior of the operating system. However, let's see this technique of Copyonwrite, the COW. We have the same physical memory page, 2 pointers which point at the same part if they have identical content. But if I want to map it into my private memory, it involves the COW, the copy. So I take it, I will have another pointer below, which is pointed to another part of the physical memory, which has nothing to do with the original one. It is way below. So let's see how we can do it. This is the whole process we're going to do. Let's see how we can map it with any problems. So I'm going to open this file and notice something. Here, what did I write? I said read and write in mode, and I think that's what's going to be the mistake. I think that was a mistake. We could assign the modifier R, or we could change it for the, let's go backwards. We could change it to a read-only mode. We could just write that. So let's follow the steps that the operating system is giving us. And then we can write whatever we want on the memory. What did we say? What we were going to do? What would I need to change in order for me to allow me to write? To allow me to write or to allow me to read. Are you familiar with this? R? I like the other way, but just let's leave it there. Okay, that's gonna enable us to open it. We said this had to match with the previous step, right? Okay, so I'm going to leave prod write in order for me to be able to write. But look at here, map shared. What are the 2 pointers in the physical memory? They are pointing at the same point. And I'm going to do something. Instead of writing map shared, I can say map private. Do you think I can do it? We have seen the definition of the function. I can write this. And what is happening here? One, there will be a copy. I will be able to do whatever I want with my copy. But when the 2 pointers go back to the same place, I won't be able to do what I wanted. But while I have this copy, I can use it as I want. Okay. You can see that there is a warning, but we don't care. If we are compiling, it is okay for us to ignore that warning. Are you following me? Okay. This is a breach, a segment breach. So this is not working. We're trying to do something that the operating system don't like, because there are some privileged systems, user identification systems, and the operating system doesn't like what we're doing. Okay, let's see if now we can advance a little bit. Let's imagine that I have a read-only mode file with permissions for everything to match correctly. And then I'm going to open it with the indicator read-only. And I'm going to use the option prod read. The operating system is going to allow me to do so because both match. It is not what I did previously. In this case, the operating system sees that both of them match, and they match with the permissions within the file. Now, I shouldn't be able to write on a read-only mode memory, but if I map it in the private memory, I could write on the file, on the copied, and I could use any function. Here we have the roadmap .c, where we could open any file, both permissions match. I have my private part, and here I could see the process memory within the prom sec mem, and with lsec I could go to a certain position, I could write, I could do whatever I want. But what's the limit? To what extent? When I tell the operating system to discard the memory and pointers point at the same part, it's going to say that permissions do not allow me to do so. Okay, I'm going to copy this to the home of the user CyberCamp. This is the owner, CyberCamp. If you want, you can copy the whole folder. And I change the user. Okay, this is a ROM map file. It is mine. I'm no one according to my ID, and I'm going to edit this file. If you realize it is exactly the same, but instead of having this file, I'm going to, instead of adding a file that I created, I'm going to open directly the file etc passwd. It is a system file, but it works in the same way. This is in read-only mode. I have the prod read, but notice this is the difference from before, because both matches and I have a private memory, and the rest I don't care. It is just to advance in the file and to show it on screen. Then we need to clean here. When we compile, let's see what happens when we compile. Roadmap.c. Everything's compiled. And now I'm going to try to execute it. Okay, maybe I'm going too fast, but I would like for those who have a laptop to do it. Sometimes a whole workshop lasts 5 or 6 hours if we describe properly all the steps, but let's try. Raise your hand if it is working. Okay, one person, good. Here, I didn't have any problems, but the operating system has underlying permissions. It has opened the file etc passwd. It has copied it in my private memory, where I can play with the file. And then here I have managed to change in the root part. But I have a madvice, a system call in order to leave the pointer in the block of physical memory corresponding to the original file. So the system has realized, okay, since you do not have any writing permission, so the root is going to stay this way. Okay, let's see if we can advance. At least we can play on a private memory, but what is it? What can I use it for? For nothing, actually. So there is an operation called madvice. In order to accept, to commit changes, we have copied the mapped memory, the page table has been updated, we have written on the memory, but notice how important it is. It says that the steps do not have an atomic nature, which means that they can be interrupted. We do not need to follow A, B, C in order. At a certain point, I can interrupt this process and do whatever I want. I could do A, C, and then B, and then D, and this is precisely what is going to create a potential race condition which will enable me to exploit Dirtica. I have a madvice function which it is going to indicate that you need to leave the pointer where it was in the beginning. But I have another function that is enabling me to write on my part of my private memory. So if steps are not atomic, I could be writing changes on the one side, and on the other side I could be calling the MADWISE system, and maybe at a certain point, that's a race condition, at a certain point the operating system is not following and we can commit to the original pointer. We could commit those changes to the original pointer. Those changes that I have written on my private memory, and that's what Dirtical does.
So within this MADWISE function, so here I can say I am not going to need that memory, so we are going to be able to invoke it little by little. So this step is not atomic. It may be called the first step, but I can call it after the second one, after the fourth one, whenever I want to. And in order to exploit it, what could we do? Well, so the idea would be to have a first thread in which we would write, and we would have a second thread ruling out the previous mapped memory. And if we are lucky in a race condition in which there are so many cycles, we will reach a point in which the changes that I've done in my private part will remain in my original file. And in order to do so, well, we've created the user already. So let's imagine that here, for example, in this case, I'm a normal user, I'm CyberCamp, I have a user ID, I'm able to move in a normal file, and I can look for things in a normal file. I'm going to have a normal ID that will be 1,000, 10,000, I don't know what's going to be. And I don't know even what group I am, but I can look for it. If I start changing this in the thread in which I can write within the memory in my private part, if I can change zeros, if I can change 1,000 by 0000, and at some point MADWISE commits the change in this race condition, what's going to be the result in the file? Come on, the room is almost full. It will be kept. It will be kept. Let's see if that happens for real. Well, basically, this is just a small exploit in which, here, for example, you can see the threads. What's interesting to us, so in order to create the race conditions, I'm going to create a thread, the MADWISE, and the write. I'm going to have two threads, MADWISE and write. What I'm going to do next, in one thread, I'm going to look for my user. For example, it would work just by changing the user ID that I have, but I can also change the group, the description, anything I want to. And that just involves writing in that thread. In the other thread, the only thing that I have to do is saying, this memory is ruled out, commit this memory and leave the pointer where it is. So the race condition is executed, and then automatically we are going to use what we've written. So let's see if that's true. So we are a user without privileges. So I have here an exploit. You also can see the code in the root. And I have here that exploit. So if I'm a user that downloads an exploit, executes it, and compiles it, I'm not going to become root, because I have to truly find out who I am. So, for example, here, this is looking for a user that's not me. That user is not me. That user is the last user I sent, or the last person that did an exploit, or this is not always going to match to what you want to, but if you really understand the code of what you're handling, you're going to be able to do anything you want to. So what are we going to do? As I have a user ID, a certain user ID, for example, here I'm the user CyberCamp. I'm going to see that I have 4 zeros because I'm the user number 1000, 1001, 1004 with 4 digits. I can even be more specific when I'm within the files. But here I'm just opening the file for the mapped memory as we've seen it before. And this is the thread that I've mentioned before. So here, in order to find who I am, I'm going to search within the file. Even though I'm inside the memory, I'm going to look for the CyberCamp user. And I'm going to see that I have an ID number of 1000. Was it the same one as before? Yes, it was, so I think so. So this is right. So let's check. For example, here I can see that I'm user number 1000. Maybe in a real system I can be the user number 3000, or maybe it can have just 3 digits instead of 4. But this is just for you to understand a little bit more the code that's behind all of this.
Vuelvo a mostrar lo que son los cambios. Esto, ¿qué va a hacer? Va a buscar CyberCamp y le va a poner 0.
So again, these are the changes. So this is going to look for CyberCamp and it's going to add 0 to.
Concretamente dentro del map.
This is going to search within the map of the private memory, the part of CyberCamp related to the number 1000. And in the other thread that I've mentioned before, that memory is going to be ruled out. Let's see if that's true. Now we're going to compile it. Before compiling it, we have to use the library, because as I'm working with threads, I need to work through the library of the threads. So let's compile. Let's create the exploit. And now we're going to compile with F3. So now this is compiled. Before executing, I click ID. Who am I? I'm the intern. I'm the intern, aren't I? So now I'm going to execute the exploit. So I didn't write any duration in the threads. They are executing themselves. I have a lot of race conditions. So we don't need to keep it for a long time running. So maybe it could happen very fast, just in the first or second execution. I'm going to click on Control C. Who am I now? I'm the root, aren't I? So now when I write the ID, I'm going to be the number 1000 of CyberCamp. The exploit has failed. Are you sure the exploit has failed? Are you?
Cuando yo entro en el sistema, mantengo el UID original con el que he entrado.
When we are inside the system, I'm going to keep the original the original information. But if I exit the system, and then I enter again in the system as CyberCamp without changing the password, when I write the password, do you notice something weird here? Do you think there is something weird? there is something here which is not for the CyberCamp user. What can we see here? The magic that we've done. Now I'm a root user. Do you want me to turn into a group? To change the group or to change the description? Do you want me to do in the system something evil, maybe? No, this is not something that we would do on real conditions. If the system would be patched, this shouldn't work. If the system was patched, this shouldn't work. So what can we do with this? Well, in the end, this is just about having some basic knowledge and understanding what there is within this code. So with this, you can start playing, for example. So let's move to another game. Let's do an exercise. So I have the exploit. So imagine that I can write, I want to change the password of the file, etc shadow to 123456. So let's make it big. Let's try the newspapers to write about us. I know, I'm joking. This is for educational purposes. Just educational purposes, of course. So let's do this exercise. Could we do this? Could we change all users with credentials in the file etc shadow to change the password and to write 123456? Well, in this case, I'm already root. If I'm root, of course, I will be able to do so, to change this password, but that wouldn't be easy. That would be too easy. So, well, let's look for the etc shadow, right? And let's see the type of permits that it has and for whom. A normal user of the system that belongs to would have the permits here. If I'm not using an operating system, if my operating system is saying that I'm not going to be able to open this even in read-only mode, I'm not going to be able to open that file, so I don't have that possibility. But this is going to work in any file in which at least I have the read-only permit. So next exercise. So this computer is 32 bytes. But what happens with 64 bytes? How am I going to exploit that? What should I do? What should I click on?
Pero es que si somos root, es que ya no tiene... ¿Para qué me voy a complicar en ejecutar un exploit? ¿Vale?
Well, if we are already root users, I shouldn't have to exploit a user. So what this person said is just go and execute it. But then I could just go and edit it. And I mean, if the thing would be to do it without any privilege. So what's the difference between 32 and 64 bytes regarding the exploit? Come on, if you find it out, I will pay you a beer afterwards. There is no difference. There is no difference at all. They work exactly the same way because I'm basing this on a system call which is native of the computer. Maybe I can do a cross compilation. I could add minus M64 and in order to generate an exploit for 64 bytes. And well, the next exercise is to analyze the exploit available in this address. So that, because sometimes what really works is the part that we want people to see, but behind that we may find many more things.
Bueno, pues vamos con el Spectre.
And nobody gives anything for free.
Ya los fantasmas pues los tenemos por aquí distribuidos.
So well, let's move to
Y vamos a ver
Spectre.
un poco lo que sería esta parte de Spectre que
We have
seguro
our
que nos
ghosts
suena.
here all over slide, and let's check
lo de
this
antes,
Spectre
eso es una vulnerabilidad del kernel, pero yo aquí estoy cogiendo y aquí estoy
system.
hablando de una vulnerabilidad que es
Vulnerability. Spectre is a vulnerability of the kernel that happens in modern cycles.
Lógicamente, pues a ver, esto lo primero que apareció
And that happens to microphones.
Y pusimos verde a Intel.
This started to appear in the Intel system, and everybody started saying that the engineers of Intel had done something wrong. But afterwards, this also affected AMD, ARM, PowerPC, and any microprocessor that executes the speculative execution in branch prediction. Have you heard of this speculative execution in branch prediction? 1, 2, 3 people. But you've heard about this, right? Well, we will see what this is about. But, well, basically, some CVEs were assigned, and this affected barely all of the operating systems, because this is not something specific to operating system. This is in the hardware, and because of the way the hardware works, no matter the operating system that you put on top, this problem is going to be on the base of everything. As we really like this type of vulnerabilities with a logo, a nice logo, because every time a vulnerability is going to be published, people look for a nice logo, and someone writes an article that nobody understands, and that's it. So, well, part of our real work is to try to understand how these vulnerabilities work in order to reply them and to solve them. But this can also be exploited remotely. There are GIT motors that work for JavaScript. Who's not using JavaScript nowadays when navigating? I do so. But in the end, I cannot see the functionalities of any website. I cannot do anything with that, so normally I end up enabling the JavaScript. And there are a lot of challenges regarding this vulnerability, and there are a lot of many things that could be done. And I think many things have been done. I don't want to point fingers, but I think that many things have been done. But, well, in order for you to understand the context a little bit, I'm going to skip some slides, and I want to explain this clearly. This is related to the meltdown part, but I'm executing this as user lamp because of the failure of the CPV. The failure is the same. So, I'm sure you are going to understand this. I'm using user LAN mode, I'm going to be a process, and I'm going to have access to everything which is related to my part of the process. Isn't it right? For example, if I'm a browser, I will have access to my whole browser. But if I'm navigating with different screens, if the browser imposes a restriction or a sandbox in a screen, I'm not going to be able to read the data that I have in the other screen or tab. For example, if I'm using Gmail in a tab, Facebook in another tab, etc., it's normal that I cannot access from the tab, from the Facebook tab to the data of the Gmail tab, because that could be a problem. We would blame the browser that I'm using for that failure. And this is what we are going to exploit with Spectre. Within the part of the user LAM, if I have a sandbox, I'm going to be want to skip the sandbox based on a failure of the CP. But what's the difference with the meltdown? Well, the meltdown is the same thing, but if I had the user LAN here, now I have here the kernel mode, and I'm going to do the same thing, the same exploitation, but at the kernel model. But kernel can access all of the processes, right? So if I'm a browser and I'm being exploited, and I have a text processor or a keypad or something like that, this is going to have access to everything, and any password that we may have in the memory and any secret that we may have hidden in the memory is going to be exploitable. So let's see what happens and why we have these failures. So I have divided this into different steps after thinking about it for a long time. But well, we're going to see how this attack works. But by thinking about the side channel, we're going to talk about the CPU, the out-of-order execution in the microarchitecture of the CPU, the process memory protection of the operating system, and if we are lucky and if we compile everything right, probably something won't work. This workshop, by the way, is just for CPUs Intel. This is one of the jokes I always make. I was saying before that it was for AMD, IRM, etc. But this was just to show you that all of the manufacturers made the same mistakes. So as we have certain instructions, let's see what we have to do. I'm not going to compile from up, down. There are specific instructions that I have to execute in the CPU, and we need to do a native compilation. So in the modifier, we are going to add the compilator marks native. Now let's see this side channel. So logically, I'm going to base on the cache memory of the CPU, and I'm going to use this as a side channel. This technique is called as Flashblast reload, but I also have a hardware. I'm going to know what a cache memory is going to do. If I have data in the cache memory and I try to access that data, this is going to be faster than going to the memory, bringing the data, maintaining the data in the cache, and giving it back to the user, right? This is something that we've learned since the beginning. So logically, I'm going to play with that area in order to see if a cache data can be accessed faster than a data that is not in cache and that I have to look for in the memory. So, but which manufacturer doesn't use cache? Do you know any that is not using cache? No, right? But this is why cache is there, in order to access fast the things. It's true that there are manufacturers that have said, well, the speculative execution, let's try to remove the speculative execution, and now we're going to try to remove the cache, and from that point when people are trying to clean the cache, they are doing it wrong. In the end, the solution is to launch new operating systems and new computers in order to solve these problems. But well, let's move to the code. Basically, I'm going to write here.
Tenemos el Spectre.
Okay, so here we have the Spectre. And in order not to make any mistake, I'm going to show you the code. I'm going to write it down here. And I'm going to skip the slides. I mean, the slides are for you to read at home later. So here I'm going to explain very briefly what this is. So I'm going to define a vector that is going to allow me to introduce 10 elements. And this is not a random value, we will see this later. And then I will have to measure the different timings. And in order to run some tests, I'm writing these arguments here. And what I'm going to do is to restart the array that I have. So I'm going to take these 10 elements and I'm going to say their value is 1 for all of them, for each one of them. And logically, this array is going to have a value of 1 each. So element 0 is going to be 1, element 1 is going to be 1, element 2 is going to be 1, etc. And here I'm going to flush. What's a flush? Flush means cleaning. I'm going to indicate the microprocessor to clean the cache memory. This is why you're seeing here something weird, which is something with slash cache flush. This is going to be used to clean the cache just for the array that I'm using. Then I'm going to introduce some data. For example, here in the position number 3, I'm going to give a value of 100. In position 7, I'm going to give the value of 200. And now, logically, both 100 and 200, when accessing some data, this data, whether it is reading or writing data, is going to be in the cache memory. But how is the element number 1, number 0, their caches are completely clean, they have nothing inside. So in this case, as I'm trying, in this loop, I'm trying to access element number 1, number 0, number 2. I'm going to be able to clean the cache, but as there are elements that are not there, it should be brought from the cache memory, from the memory. And if this works, and if our microprocessor is vulnerable, well, not vulnerable because it is actually a characteristic of all microprocessors, this is going to allow me to know the accessing time. So, well, now I'm going to first I'm going to compile. I'm going to write access time. And that's it. And now let's see if this is true. Okay, so access time. This requires parameters. I'm going to write 1. So this is going to be useful just for one test. So I'm going to write 1 here. So what are the elements that had different values before? Which elements had different values before? Do you remember? Can you check that in the code that you have there? In the element 3, I have here 124 cycles of CPU, which is very low compared to the other ones. But what timings are you going to get in your computers? They are going to be completely different. It depends on your computer. It depends on your processes. This is going to change depending on the computer, but probably when I have a cache, a data in cache, I'm going to be able to see that times are going to reduce
Fijaros, el elemento 3 y el elemento 7, que eran
more or less, but the timings are going to reduce. So take a look at element 3 and 7, in which we've read the data. Element 7 I have 559, element 8, 238. So if I see that, I'm not going to be able to compare because I don't know what's going to happen. But anyway, I'm going to click on execute. I'm going to execute this for 1,000 times.
¿Me cambia la cosa? Sí, ¿verdad?
Does it change after a 1,000 time execution? Yes, right? Now, which are the elements with less CPU cycles? 3 and 7, right? So next time I'm going to change 6 and 4. Is it working for you? I can see that it's working for me. Someone is saying yes. Your microprocessor is vulnerable. No, it has cachet. Is it working for you all? I'm sure that it's not working for all of you. Because this is not a very specific technique in order to make sure that this is true. Because, for example, there may be data or that maybe we're not in cache. And so we are getting closer, but we don't know yet. We cannot be sure in order to continue.
Esto es lo siguiente para poder descubrir. Nosotros lo que yo voy a intentar va a ser fijar.
So, well, this is the next thing that we have to do. What I'm going to try to do, well, I'm going to skip some slides because we don't have a lot of time, but now we're going to try to set a threshold value specific to each computer in order to find out if this data was in cache or in memory. But this is going to be, of course, a rough value. For example, if we have more than I don't know how many cycles, or if it lasts more than I don't know how many seconds, I'm going to guess that this is in cache. If not, this is going to be in memory.
So now, I'm gonna share, we're gonna save a secret or a password. Normally, we shouldn't access a secret value from the outside, but I could do some cleaning, I could reload what I wanted, and I could check these cache memories in order to see if the secret, maybe in the element 0 I have some value, in element 1 another one. Our basic idea, in order to recover a byte, how many values do I have? 256, right? Maybe you had written capital T or whatever. What's the problem? If I define an array of this kind, it won't work. Why? Because operations in storage cache, in caching, works in blocks, not in bytes. It works at the block level, not at the byte level. I have a block for this part, another block for another part. So the idea when using the side channel is that every element has to fall within a certain block in order for me to be able to check later that block and to be sure that the element with the lowest time access in each of the blocks is the element of the secret I was looking for. That's the idea of Spectre. So what am I going to do? Why was I using the value 4096 bytes? In order to be sure that each one of the elements is going to fall into a different block. So I'm going to create the array of search in order for them not to match, because we will have some problems with element 0. When I'm looking for that element 0, I have some problems. The element 0 is kind of special, so I can add a delta value. So if the element 0 is going to be here, I am going to send it to 1024 bytes in order for it to act as the element 1. But instead of going from 0 to 10, I will go from 0 to 11, knowing that 11 will be the 0 element. I don't know if you're following me. That's why we're going to add a delta value. We have another code line, which is flash reload, and basically, oops, I'm sorry.
Aquí lo que estamos haciendo, pues, definir. Aquí lo que estamos haciendo, pues.
What we're doing here is to define the secret value in order to save it. Let's, for example, say the number 13. Out of superstition, I'm going to define a delta 1024, and randomly, because I just wanted to do so, I defined a threshold. So let's say it is a threshold of 80. I just made it up. What do you think if I write 100? What if I type 1000? What value do we enter? Less? No, that's dangerous. If we read all the documentation on microprocessors, there are thousands and thousands of pages that tell us that threshold, the values that we can enter according to the threshold. If I enter a very low value, maybe it won't be useful. So I am going to use a statistical technique in order for that value to be closer. So I'm going to repeat the search for the secret, and with a small counter I can determine how many cache hits I have. I can repeat it 1,000 times or 1,000,000 times, and I'm sure that if after 1,000,000 times the value is cache, we find that the element of the array was in cache. That's the element we're looking for. So that's why that value should be around 80, 100, and here we have the array in order to prevent I do not want to fall it right next to it, because if the element I'm looking for within the same block, I cannot distinguish it, and the rest is kind of easy. So the only thing I'm going to do is to do a flash reload to call the system function, and then I'm going to do the reload of the flash side channel. Let's see if we can compile it. The native and the flash reload. .c. Let's see what happens. Let's execute it. Voila.
El secreto ha recuperado el 13. El secreto ha recuperado el 13.
So secret recovered the value of 13. Is it working for you? I hope somebody tells me no. Okay, one over there. Anyone else? Maybe a second person? The rest of us may have more vulnerable microprocessors. I need people to tell me, hey, you recovered the value 13 because it is your machine, you know the threshold value, and so on. Once you have compiled it, what we're doing is we're refining a little bit more the code. I am sure that at the end of the session, if I manage to end on time, I am sure that you will recover the secret value. Is it working for you? That means your microprocessor is a bit vulnerable. And it is a new laptop, I can see. Maybe 15, you bought it 15 days ago? Really, I really need someone to tell me it is not working for them. Why did it work here? It was luck, actually, because if you start doing this, maybe one of them work and some others don't. And maybe after 1 million times, you can recover the secret value of 13. Otherwise, maybe I will need to make some efforts and to improve the code so that I am sure this is working in a universal way for every kind of microprocessor. So let's continue while you're working on it. And yeah, let's move on. Okay, so we check it is not... I can play with threshold values above or below, and we're getting things a little bit more complicated. You can search for a threshold value that guarantees 100% of hits in cache memory. Sorry? Only one. Okay, yeah, that's precisely why I'm telling you this. We cannot be sure of a 100% value when we want an exploit to work in a universal way. So what can we do? We need to keep on thinking on it, and we have other things to think about. It is the execution and the branch prediction. This is a code we learned in our first year of training, right? In this code, data value equals 0, and it is going to verify if the value is lower than the side and the increase of 5. Let's enter x equals 3 and size equals 10. So the code is if 3 is less than 10, then data equals 5. Is that correct? Okay, good. How can we execute this simple code within the microprocessor? The microprocessor is not stupid. Microprocessors and engineers who are very smart decided to execute the good part of the branch, of the jump, at the same time that I execute the bad part. When you end the verification, I am going to show you only the part that you want to see with data equals 5. But wait, maybe we can say, stop it there. If at a certain moment and if is halted and we were able to open the microprocessor, I would have the execution of the if function and the execution of the no function with both results. And this is precisely the execution out of order and branch prediction. And why have we carried out a branch prediction? In order to obtain results as soon as possible. And Spectre and Melden were based on these kind of foundations, which I mentioned earlier. So what microprocessor manufacturer didn't think of this speculative execution? If they hadn't thought of that, they are stupid, because the faster and the more optimal the microprocessor works, the better. Okay, so this condition is true outside the CPU, but at an architectural level, we could see if it had been implemented or not, and I could start seeing those results. Any microprocessor enables us to execute this out of order, because what we want is to give the microprocessor some instructions to be executed at the same time, depending on the functions that we have. But in order to execute an if function, this is enough. And now I'm going to execute a sandbox. What is a sandbox? What does a sandbox do? It executes the if function. So if you are on this tab, you cannot access the data from another tab. And if you are in the other tab, you cannot access the other tab's data. A simple sandbox regarding the code level, we can have a part of password with a secure function to access it. And I'm checking it with an if we have access or not. In this case, at the microarchitecture level, it is going to execute functions speculatively. The prediction is going to be true or false, and changes are going to be committed. And now we could somehow try to exploit the code that we had before with this. What was the error of this execution regarding design? If it had to process something and an if function needs to process something, what didn't we delete? The data from the cache. So we should have done a flash. But who was going to access the data from the cache? Who was going to check the microarchitecture from the CPU in order to see what was executed or not? Well, there are 4 Chinese who launched the paper, and the 4 stupid persons who devoted their time to read those documents. So maybe here we can see how we can see that execution in order to see the microarchitecture. So let's go back to the code here in order for me to explain it better for you. Here, notice that it is still the same, but we are adding a bit complication. This is not machine learning, this is not AI, this is manually refining the code. I keep on doing the flash, reload. I see here a victim function. This is a victim function, whatever it is. If x is less than some value, let's see if it executes it or not. Let's see what happens. This is like Pokemon. We're going to train the CPU in order for it to adapt the true function from the victim function. I'm calling from 0 to 10, and I am calling the function victim, the victim function. Is that right? But before calling the victim function, I am cleaning the cache. Be careful, because the victim function, let's imagine we set the threshold, the maximum value of the victim function to 5, or lower than 5, or higher than 5. When I am calling the function is going to tell me true, 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 and then false, 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 false. And the victim function is going to process something, right? Maybe some instruction, but I'm sure it won't leave any data. I'm sure it will leave some data in the cache memory. And if I look it up, or if I call the function correctly, I mean a normal execution, maybe not victim function, but any other function, when I call it and I reload the side channel, the result is going to be true, but in that, out of all the execution, probably I would know what is true, what is false, and then I can look up in the cache the data that were left here. And that's what this code does. Let's compile it and see if it works correctly. So we enter here native and see what happens. Let's execute it. The victim function, I was calling it from the value 97. Okay, let's see if we have the value 97. Oops, what is this? What is this? Maybe I should have received some results, some value, right? I mean, you have the code, right? Okay, so yeah, I was saving it, I was reloading. At least I should have received that line of code. Yes or no? What do you think? 97. 97. Who is sure about it?
Fijaros de qué depende.
Notice that it depends on some values. If it is on cache memory, I was entering a cache threshold. So in this case, we can compile again. In the hacking, in reversing, in exploiting, in everything, you need to be lazy. Why to compile again? No, I'm going to... Oh, look, this is working already. It's always working, and it is going to... And when is it going to stop working? I have no idea. I'm clueless. I don't know when it is going to work in a universal way, or when I'm going to have a good value. But I told you before that with a threshold of 100, I do not have enough warranties to make it work in every microprocessor. So if it is very precise, it's going to be very, very difficult. This is basically what we're explaining here. Okay.
Todo esto, pues, vamos a tener la predicción.
Okay, so here we have the prediction. The speculative function is executed. Sometimes it does work, sometimes it doesn't. It depends on the machine. And I would like you to do this afterwards. Because in the main, let's imagine we remove flush. In order to see that maybe we can never find it, but maybe if we train it and we call with some set values, we can realize it is more variable. Sometimes we will only obtain this result once in every 100 times. But at least I know it is stored in cache memory. I still have some noise, and that's the reason why it is not working. There is some extra data stored in cache. So now I can make the code to execute the true branch, even if the condition is false. The CPU won't matter. So if I do not clean the cache, I will have a vulnerability. So what does Spectre do? I have secret data within the same process, but there are some functions within the same process that do not have access to those data that we had saved. So what happens here? That I have a protection at the hardware level. And this protection, since it is from the same process, it is a software protection at a sandbox level. And here we have the same problem. I am going to create a sandbox. I will have a restrained access area and other with no restrained access. I can call the function with correct values in the beginning or incorrect values. I can train the CPU to leave some data in cache or not. Can I access? No. Can I access? No. So maybe the value is 97 and cache is going to say yes or no. Is it 100? Is it 110? Is the element 13? And from there I'm going to recover everything as logic says. I'm going to start here a buffer. I'm going to create the sandbox. And basically I would have a secret on the top. I would have a very, very simple sandbox, but do not think that sandbox from browser tabs are more complex than this one. And I am going to be able to access from 0 to 9, depending on the value, if it is lower or higher. There we have the whole code. I am defining here a secret. I have powered, I have a sandbox, and the rest is the same. So when you do this at home, use values from 60, 80, 100, and 120. You don't need to enter 5,000 pages of the text spec. And that would be enough. And now I'm going to try to train my sandbox. I'm going to execute a flush. I'm going to call the function with whatever I want. And finally, I'm going to see this. Let's see if it is correct. And now I would like you to... I don't know where you were, those who didn't get the correct value, but now I would like to see if it works or not. This is what we have done. Well, the code, I mean, the code I showed you. And that's it. Will it work? This is already a Spectre. This is a Spectre. If I did the same with a leak of a device with a kernel, I would have access to all the memory of all the processes. It would be the same. So I'm going to compile it. I'm going to compile native. I'm going to originate the Spectre. And
venga, nos comamos una cervecita.
Let's see.
¿A qué sale? A todos.
Do we bet something?
97
Do we bet on a beer if it works? Does it work for you? 97 was the value, wasn't it? But now I want those who couldn't do it before to speak up. Okay, let's press enter all together. Let's do it. But didn't we have to obtain the value 97? What's the value you're obtaining? It doesn't compile? But you have it on the top, the compiling button. No? Is it not working for you? Are you receiving the value 0? Okay, let's press enter several times. Because, oh, look, there are different values here, 115, 115, 0, 0. I want you to see it by yourself. You don't need to compile it 1,000 times, but press it for several times. 115 is the value for non-capital S, but sometimes you get the value and sometimes you don't. So it's almost Spectre, but not yet. Right? Do you understand? Are you following me? Are you following me? Yes. Okay, so in fact, this is the code when we called. This is the secret, and if we use a browser and we search who does have internet access, because I do not have Wi-Fi access, this should work always, but I see that this works randomly. So, what to do? Do you have any ideas? Because I have some. Let's imagine port JavaScript. You might think if you want to do it for browsers. This, I could execute it several times. I would have some data. You can realize that the value 0 appears several times, not only in my computer, but I'm sure that in yours as well. I distracted with the rickroll, with the video, and then we could discard the 0 value and execute it several times, right? Is that correct? And then I would have the value 115 in this case, or whatever value it gives us. Is that correct? Okay. So, let's see one thing. This is full of noise. It's not useful at all. We have additional values. We can use it later. I have caches working. So why not to call a statistical function? I can launch the attack several times, but I can set a counter with cache hits. for the element 0, 1, 2, 3, 4, in order to recover the secret of a value, and then of a byte, sorry, or for whatever I want. And then simply with this statistical function, which is a very simple one, I can check the element with the highest number of hits. This is quite complex to add a counter. For those of you who love games, we have a scoring counter, and every time a hit is obtained, then the counter will keep on going up. Let's see if this is true. Okay. Let's do this. Directly we can do this. We have this exploit. I have the secret. I have the sandbox. I have everything as it was before, and the only thing that we did was to add one and launch it several times. Let's compile it. GCC architecture native exploit.c. Okay. Now I have my counter, my scorer, and I want you to execute it.
What's the result? Do you get the S? Those of you that couldn't get it before, this is not magic. We just had to check the hits of the S element. Are you obtaining the same result? Well, so instead of paying the beer for you, I think that you will have to invite me. Well, for those of you that are watching through streaming, let's see if this is true or not. As you've seen, it takes longer. I mean, we don't have to wait for the whole read roller, but besides the memory address, which I've obtained because I wanted to, some of you will understand why later, I'm obtaining the 150 value, the secret value, which corresponds to the letter S. If I execute this right now, and I don't know what the result is going to be, but if you execute this now, you're going to obtain different results. But it's working, right? Now I'm able to access a part to which I couldn't access before, and here I may find a password that I've kept or anything. I mean, this can be data from a picture. Use your imagination. And now how can I give back all the information that the secret has given me? I don't know if I can see you well, but... Okay, I'm going to repeat what someone just asked, because we don't have a microphone there, but he just mentioned one of the possibilities, yes. Please listen to our colleague. If you know where the byte is with the secret is kept in the memory, you just have to edit the memory position and run the process. That's it. You don't have to do anything else. Please, a big round of applause. This is why I've linked the memory address where this was hidden. So yes, I will invite you. I will pay a beer to you. But well, I have a hit counter, right? If I show the element with the highest score, which was 115 in the next element, what will I have? Same thing, right? I can access through the memory or through the hits counter. The element with the highest number of hits, and then the element with the second highest number of hits, until the final secret picture that you may have in the key past. Well, maybe that's not possible, but passwords or things like that. So this would be used in order to recover that information. For example, here let's write something. We have a bonus here and a second exploit. So now we have more Spectre sources. If we read this, what is this doing? Exactly the same thing that we did before, and now I'm going to be able to understand it better. I'm going to generate a second exploit here. So this is my second exploit. LSTD exploit 2.c.c.
Para seguir, native no. Habéis visto que si no le ponemos el native, precisamente cuando intentamos invocar eso,
well, if we have to delete that native because otherwise this is not going to work. Otherwise, so well, we have our second exploit here, and well, here we had a secret. Where was it?
Bueno, un secreto por ahí, no sé dónde, no lo veo. El del Spectre, ¿no? No lo veo. Está.
Where is it? The Spectre secret that we had.
Ese secreto que tiene un chorrón de letras, pero bueno, es que ya hemos revelado cómo se podría coger y cómo se podría hacer.
Well, this is the secret with a lot of characters. We've already known, we've already discovered how to work with that, and once it's compiled, when we execute exploit 2, if we go up, down, we can see that here we have the address, the scoring. So I've revealed a secret through Spectre. This may be a password or anything. We can use our imagination in order to work with this. But basically, in this case, and with type of workshop, what I want to do is for you to understand the different steps, and to also to try to resume something that it is very complex to understand. I mean, this is the objective, the purpose of my workshop today for this CyberCamp edition. I'm talking at the user level, of course, but now at the kernel level, we also have to do some things, right? Can you imagine what are we going to be able to do at the kernel level? This is going to be the same thing, basically. So, well, I'm going to continue with the slides. I'm going to skip the meltdown slices. I think I'm going very fast, but I'm sure that this rings a bell to all of you, doesn't it? Of course, this is familiar to all of you. Here, for example, we are working with a kernel module that we are introducing that's protecting a special driver, a special process. A normal user wouldn't have access to this. But in the end, if we read the slides, we're going to realize that the process is exactly the same. We add information to our counter, and that's it. And in order to get everything back, we are going to follow the same process. We still have some time. I didn't think we would make it, because I know that this is very complex, and of course I would like to thank you for being here and thank the organizers of CyberCamp for doing this. But I think we have time for a couple of questions, so we have a couple of minutes. If you have any questions, please feel free to ask them now.
Para sistemas operativos Windows y Linux que estuviesen en procesadores AMD.
For Windows and Linux operating systems that are in AMD operators, does it work the same? Same thing. This is the operating system is not important, because the problem is based on the design of the CPU. There are also patches from Meltdown, etc., that slow the operating system, because what the microcode of the CPU is not doing is now being done by the operating system. So, taking into account all the flashes written, etc., the system is going to work worse. And I'm glad that we've mentioned ARM, because this has been, in the end, a copy of a copy of a copy. So regarding the speculative execution, this is something that must happen, that must be done, because we need to be more efficient and faster than our competitors. For example, Funker. Everybody wants to be the best in their category. Are there any more questions? Nothing?